Take a specific gold-copper pyrite mine in China as a case study for the legacy mining dilemma. The site processes complex ore, averaging 10 to 20 grams per ton of gold mixed with heavy copper and iron impurities. This chart tracks their historical output. Despite the 10 to 20 gram ore grade, their recovery rate hit a hard ceiling at 70% using traditional mercury amalgamation. Mercury amalgamation historically appealed to these sites because it requires incredibly basic equipment and almost zero initial footprint to get started. It is an efficient way to start. You feed in low-grade ore, and it produces a 30% grade amalgam that can be refined directly on site. A 70% yield with low overhead looks like a functional setup on paper. But that simple infrastructure masks a catastrophic and terminal liability. Mercury pollution spreads through local ecosystems, causing long-lasting environmental devastation in the surrounding air, water, and soil. For the on-site workers, direct contact with the amalgam poses extreme and immediate toxicity risks. Global regulations are catching up. The Minamata Convention is the definitive mandate, now rapidly outlining the use of mercury entirely. Most operators know the mercury flowsheet is a dead end, but they fear that modernizing will bankrupt the operation. The central concern is capital expenditure, the assumption that a transition requires ripping out every piece of existing infrastructure to start over. Finding a way forward isn't a choice between environmental protection and profit. Pragmatic operators are finding ways to modernize that skip the CapEx trap completely. To replace the system, we have to look at how it's built. Traditional processing uses two primary pathways, internal and external. In internal amalgamation, mercury is added directly into the grinding equipment to capture coarse gold while the ore is being crushed. This process is integrated into the heavy machinery already installed on your site, like your primary ball mills. External amalgamation extracts finer, free gold outside the grinder, using mixing boards, classifiers, or bushy machines. Both methods rely on the same physical reaction. Au plus 2Hg yields AuHg2, forming a solid mass. That solid amalgam then requires dangerous heating to volatilize the mercury, leaving behind sponge gold. Notice that the physical hardware, the mills and the boards, performs well. The operational failure is isolated entirely to using liquid mercury as the solvent. That distinction is why JIN CHAN metallic ore dressing agent was developed. It is a modern, low-toxicity chemical alternative that replaces the toxic solvent while keeping the hardware. Economically, it functions as a one-to-one drop-in replacement for mercury and traditional cyanide. This comparison matrix evaluates mercury against JIN CHAN across 4 critical vectors: CapEx, regulatory risk, recovery potential, and worker safety. Because the new agent uses your existing physical equipment, your CapEx stays flat, while your regulatory risk and worker safety metrics immediately optimize. The primary operational change is technical. Your staff will need to manage chemical leaching times rather than physical amalgamation queues. By swapping the reagent, you achieve 100% environmental compliance without purchasing a single new piece of processing hardware. The physical transition follows a 3-step roadmap. Step 1 is the equipment audit and decontamination phase, where you must thoroughly strip and flush all residual toxic mercury out of your existing barrels, mixing plates, and ball mills. This deep cleaning phase is the only period of operational downtime required during the entire transition. Step 2 is agent integration. You fire up those same newly cleaned legacy machines. The JIN CHAN reagent is introduced directly into your current classifiers or external mixing boards, activating high-efficiency leaching, capturing both fine and free gold directly within the slurry. That brief pause to wash out the tanks is the only friction point in fully modernizing a toxic legacy flowsheet. Step 3 is baseline optimization. Let's return to the China case study, where the site was historically limited to a 70% recovery mark. When you move from amalgamation to modern leaching, that old 70% ceiling becomes the new minimum floor. Because the chemistry is more efficient, operators run iterative tests on complex ores to capture gold that previously remained trapped in the tailings. The output is exactly what the market requires: high-purity, refined metal, poured on-site. Switching to modern leaching chemistry ensures regulatory compliance, while reaching extraction efficiencies that physical amalgamation could never achieve. This quadrant chart maps the strategic landscape, plotting capital investment against regulatory and environmental safety. The traditional mercury method sits in the bottom left. It is cheap to run, but fatally dangerous and illegal. Building a new cyanide facility jumps to the top right. It provides safety, but the high capex is often too steep. The JIN CHAN transition occupies the top left quadrant. It combines low hardware costs of the past with future safety standards. This strategy specifically addresses the needs of operators currently hitting recovery ceilings with their legacy infrastructure. Modernizing your flowsheet provides an immediate zero capex upgrade, utilizing the exact tools you already own to ensure both safety and profitability.